3, 2, 1. Okay, so far, where we are, what we have discussed. We're discussing Brayton cycle, it's a closed cycle, gas turbine engine. We have done the following topics, and we have some to go. We have introduced the topic in a video. We have done the energy analysis, thermal efficiency calculation, and the derivation of it. We have done the compromise, and we have discussed the compromise between network output and the thermal efficiency in the previous video. Today we're gonna discuss the deviation from ideality of the cycle, and then we have another 3 or 4 videos discussing the development of the cycle itself. How we're gonna improve the efficiency even more by adding some more stages and exploiting some of the heat that we dispose to the atmosphere. Okay, by the regeneration, reheating, and intercooling development stages. That's what's left over. Today, we're going to discuss the deviation from ideality. This is the ideal cycle on a TS diagram. This is a very ideal process, assuming that this one is isentropic, it's perfectly isentropic, isobaric, isentropic, and isobaric. Having the arrows pointing, as we agreed before, in the clockwise direction, because it's a power generation cycle. Okay. In real, this cycle does not go like that. It goes a little bit different. How it's different? The first part, the process 1-2, it's not perfectly isentropic. There is some deviation from the isentropic behavior. It ends up somewhere in here. First of all, we have to put some constants in order to discuss the deviations with respect to this constant. First constant, we're gonna make that we operate between these two pressure limits, between those two pressure isobars. This is P1 and this is P2. Some things we're gonna discuss their deviation, and some things we keep as constant, like T3 and so on. The second deviation is that the heat addition is not perfectly isobaric. There is some pressure drop in the heat exchangers. So it's not perfectly like this. It's somewhat like this. And we reach over here. The point, the state subscript S, denotes the theoretical one, while the A denotes the actual one. This is 0.3, is T3A. And as before, the expansion is not isentropic. There is some deviation from isentropic behavior. There is a pressure drop over here, and the heat exchanger also, so it's ending somewhere in here. So the cycle ends up with less area included, thus less actual work output compared to the theoretical one. The pressure, the work exploited in the compression is more than that of the theoretical. The theoretical is from T2S to T1, while the actual is from T2A to T1. Then we might define some isentropic efficiencies for the turbine and for the turbine and for the compressor. First of all, let's write some notes over here to sum up all the deviations. The first deviation we've discussed is the pressure drop. Here is the pressure drop. Also, we have one over here, from here to here. Okay, the second one we have discussed, the deviation from the isentropic behavior. Thus, we're gonna define some isentropic efficiencies for the compressor and for the turbine. The isentropic efficiency is the actual of the compressor, of course, of the isentropic This is denoted by as if it's its second law efficiency of the compressor is equal to the work compressor theoretical over the work compressor actual. We know that the actual one is greater, so this ratio is always less than 1. And in the theoretical limit, it's equal to 1. So this equals to H2S minus H1 over H2A minus H1. So it's equal to T2S minus T1 over T2A minus T1, where CP's cancels out. That's what we're left with. Another efficiency is defined for the turbine. The turbine is a little bit different because I'm the one extracting the power. So my theoretical limit is the upper limit, while I'm gonna extract some more. The actual is less than the theoretical. Theoretically, I'm having the limit, the best performance I want from the cycle. So it's gonna be the reverse, the theoretical one, which is the actual one, which is a smaller. The actual work of the turbine over the theoretical work of the turbine. Theoretical work out. In the compressor, I'm the one exerting the work. So my theoretical limit is the least. It is the least amount of work I'm gonna do in an ideal work to compress this air with this amount. Thus it's H3 minus H3 what? This is the actual one, it's 3A minus H4 minus H4A over H3. That's H3A is the same as H3S because this is an ideal fluid and both states are at the same temperature. So we have agreed before that all the thermodynamic properties of an ideal gas are defined using just one quantity, which is here the temperature, T3. Thus over H4A over H4S. Then we need actual over theoretical. That's right. T3 minus T4A over T3 minus T4S. This is the isentropic efficiencies that we have come to a conclusion after the efficiencies that both efficiencies are less than or equal 1. Thus, the work actual in the cycle is always greater than equal for the theoretical or the ideal state only, the theoretical work in. And the work actual turbine out is always less than or equal to work theoretical out. This is the conclusion of our discussion, and that we knew that we have some efficiencies that we have to take into account when calculating and tracing the states of a cycle of a cycle with efficiencies and somewhat actual one during problem solution. Yet we have to come the development, regeneration, reheating, and intercooling in the following videos, inshallah. Thank you.